Section 8.3 is testing a claim about a proportion. What we're going to do in this section now is make use of the skills that we learned in 8.2, that we've mastered from 8.2, that we recall with perfect clarity from 8.2. So what we're going to be doing now is testing a claim about a proportion. The test statistic, if you'll recall, is different for each different parameter that we test a claim about. We're focusing strictly on the proportions this time. In order to test a claim, we need two things. We need a null hypothesis and we need an alternative hypothesis. Our null hypothesis takes the form of a parameter and then a symbol in between and then a number. So does the alternative hypothesis. On the null hypothesis, what symbol has to go between the parameter and a number? Equals. With the null, it always contains equality. The alternative never contains equality, so we have some choices. We could do greater than, less than, or not equal to. The greater than would yield a right-tailed test, less than a left-tailed test, not equal to a two-tailed test. We end up with a p-value. I'm just kind of refreshing your minds here what's going on. The p-value is what? Right, the p-value is the probability that we reject the null hypothesis given that the null hypothesis is true. That's also called a type 1 error, and alpha is what we use to represent that type 1 error. It's called a significance level. So there's two basic methods that we're going to talk about for testing a claim about a population proportion p. Now this p right here is not the same as the p on the p-value. The p-value is actually a probability. The p-value is a probability. It's the probability of rejecting the null hypothesis if the null hypothesis is true. The notation we use for the p-value, no matter which method we use, either the p-value method or the critical value method. The notation n is our sample size. P hat now is our proportion from the sample. Remember, if there's a hat over it, it's a sample statistic. How we get that is we take the number of successes divided by the number of elements in our sample space. Remember, x is the number of successes. And then p is our population proportion. Q is 1 minus p. The p here and the q come from the h naught. Now there's some requirements that have to be met in order to test a claim about a population proportion. First of all, as always, we have to have a simple random sample. The conditions for the binomial distribution must be satisfied. Do you remember what those are? Fixed number of trials, only two outcomes, trials are independent of each other, and the probability of success remains constant for each trial. Also, the conditions for the sample size have to be met. N times p, the number of successes has to be greater than or equal to 5, and n times q, the number of failures has to be greater than or equal to 5. This way, the binomial distribution of sample proportions can be approximated by a normal distribution where the mean is n times p and the standard deviation is the square root of npq. This condition here assures us that we can use a normal distribution regardless of the original population's distribution. This is our test statistic that we're going to use, but remember, we don't worry too much about that because we're going to actually use the graphing calculator to conduct the tests for us. This is the caution that I was warning you about. The p-value is different from the population proportion. This is the percent of successes. This is actually a probability. It's a probability of getting a type 1 error. When we use the TI-84 to conduct a test of hypothesis, we're going to end up using the one proportion z-test to get to the input screen below. And these are the keystrokes that we use on the TI calculator from the home screen in order to get to the one proportion z-test. If you will hit stat, hit the arrow to the left, and go down to number 5, you'll get to the one proportion z-test. Let me just show you right fast what that looks like. We hit stat, go to the left to look at the list of tests, and then number 5 here is the one proportion z-test. And when we do that, we bring up a screen that looks like this, that I've copied into your notes. After we do that, then we're going to input the p, the population proportion, from the null hypothesis. That's the first thing that this is asking for right here. This is a 0.5. This is a value from the null hypothesis. It's the number from the null hypothesis. X then will be the number of successes from the sample. N is the number of samples. And then you need to select whether or not you want a left-tailed, right-tailed, or two-tailed test. That's this last column down here. And then you're going to select calculate. The output screen then looks like this. And this is based on the XSort sample data that we used in 8.2's lecture, where we had 58 girls out of 100 births, and we wanted to test the claim that the percentage of girls is greater than 50%. If the XSort method worked, we would end up with a proportion of girls greater than 50% that we would expect to get due to nature. The output here, this tells you the name of the test. This tells you the alternative hypothesis. This is a right-tailed test. This number right here actually is the p-value. And then there's your p-hat and your n. Remember, for this problem, we were testing the claim that the percentage of baby girls born using the XSort method is equal to 0.5, meaning it made no difference on nature. Our alternative that we wanted to test was no, that XSort method actually increased the likelihood of having a girl. So we would have more girls born. Looking at this p-value then, we would say, no, that p-value is bigger than 0.05. Don't confuse the 0.05 and the 0.5. I know the numbers look similar, but that 0 makes all the difference in the world. This is the probability of getting a baby girl. This is the probability of rejecting the null hypothesis, assuming that it's true, based on the 58 girls out of 100 births. If we were to look at the graph of this, we would have our normal distribution, and our test statistic is z equals 1.6. So that means that over here we've got our test statistic at 1.6, and this area right here in green is 0.055. Our critical region that we didn't mention here is our alpha, and that's actually this area right here. Alpha is equal to 0.05. Because the alpha here is smaller than the p-value, that means that our test statistic right here fell in the clear, and we would fail to reject the null hypothesis. This is the p-value method when we compare p-values with our alphas. If the p-value is greater than or equal to alpha, we would fail to reject the null hypothesis. However, if the p-value is less than alpha, then that means that this test statistic would have fallen over here in the red, so that we ended up with a smaller area than alpha, and we would reject the null hypothesis. Do we ever accept a null hypothesis or prove that it's true? Good. You don't do that, and I beat that into you enough on Tuesday that you're answering correctly and quickly. That's good. Now, the critical value method will yield the same results, but what it means is I need to find this critical value right here, and how I find that critical value is I'd use the inverse norm. And the inverse norm, this 0.95, ends up being the area that's to the left of this critical value. That's z sub star. So that this area right here is 0.05. And that ends up being 1.645. On a right-tailed test, meaning your rejection region is here to the right, we would fail to reject the null hypothesis if the test statistic, this is the test statistic, is less than the critical value. And this is easier to see if you draw a picture. With a test statistic of 1.6, we would see that our test statistic would fall right here, 1.6, and it would be less than 1.645, the critical value. It's easier if you draw a picture, compare the numbers, and if your test statistic is in the clear, we fail to reject the null hypothesis. Otherwise, we would reject the null hypothesis. There is a third method that uses what we did in Chapter 7, and that is the confidence intervals. Here we would use the 1 proportion z interval. This is the input screen. This says interval instead of test. When we were doing a 1 proportion z test, the last words here were test. So you'd input the same data, only now you have to determine the confidence level, and there's your output. Now, one thing I want to point out is if alpha is equal to 0.05, we end up having to do a 90% confidence interval, because remember, the confidence intervals take away area from two tails. On a confidence interval, if you want to use that information to compare a right tail test, that means I need this area right here to be 0.05 and this area right here to be 0.05, so that I would have the area to the right be 5%. That corresponds here. if using a confidence interval to test a claim of a one-tailed test, double the alpha for finding the confidence level. When I say double the alpha for finding the confidence level, I'm referring to this number right here. If alpha is 0.05 for the test of hypothesis, our confidence level would be 0.9. What we do to test that claim for our null hypothesis, p equals 0.5, against our alternative hypothesis, p is greater than 0.5, I look at the results of the confidence interval right here, and if 0.5 is in there, I have to fail to reject the null hypothesis. Because remember, the confidence interval gives us the range of plausible values for that parameter. And that means that 0.5 is plausible because it's in there. Now, granted, it's close to that end, very, very close, but it's in there. Remember, this test statistic was very, very close to the critical value. We still fail to reject the null hypothesis. This p-value was very, very close to our alpha level, but we still failed to reject the null hypothesis on all three. The confidence interval is not as scientifically accurate as the p-value test and the critical value method. So if you have discrepancies between the two, go with the other two tests. So when testing claims about a population proportion, the traditional method and the p-value method are equivalent and will yield the same results since they use the same standard deviation based on the claim proportion. However, the confidence interval uses an estimated standard deviation based upon the sample proportion. Consequently, it is possible that the traditional and p-value methods may yield a different conclusion than the confidence interval method. A good strategy is to use a confidence interval to estimate a population proportion, but use the p-value or traditional method for testing a claim. Confidence intervals for estimation, p-value and traditional for testing a claim. So here's another problem, and we're going to use different methods to solve it. It says, based on information from the National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. In a random sample of 400 scanned computers, it is found that 380 of them, or 95%, actually have antivirus software. Use the sample data from the scanned computers to test the claim that 93% of computers have antivirus software. What is our claim symbolically? We would say P equals 0.93. So our null hypothesis is in the claim. Can we prove this is true? No, all we can do is prove that it's not true because our original claim contains equality. So now we need to check our requirements. First of all, the 400 computers are randomly selected, so our sample size is sufficiently large. We have enough successes and enough failures to use the normal distribution to approximate the binomial, and there's a fixed number of independent trials. All the conditions of the binomial are met. We are okay. For the p-value method, and for any method, you always want to begin by identifying your null hypothesis and your alternative hypothesis. Our null hypothesis will be p equals 0.93. What will our alternative be? Not equal. We just want to know, is it different? Not is it more or is it less? Even though our samples indicated it's more, they just asked, we're just testing the claim that 93% of computers have antivirus software. The opposite of that is no, they don't. So using the p-value method, we are going to go to our calculator, and we're going to input some information. What am I going to put right here for P naught? This is a 1 proportion z-test. This is the value from the null hypothesis. X is the number of successes. What are we calling a success here? Having the software. So how many successes did we have? Out of how many computers? And what did we select for our alternative hypothesis? Not equal to. So now we calculate the results. And here's the output. By the way, did they tell us what alpha level to use? No. So what do we assume alpha is? 0.05, always. What is our p-value here? 0.117. Based on this p-value, would we reject or fail to reject the null hypothesis? Picture if we're having trouble seeing this still. Our rejection region is going to be evenly split over two tails because it's a two-tailed test. And we have a p-value of 0.11. Our test statistic is 1.57. Our test statistic would actually fall somewhere over here. There's 1.57. The p-value is the area to the right and the area to the left of negative 1.57. But either way, we're in the clear, aren't we? So we would fail to reject the null hypothesis. Now I said you never want to stop at that point. You want to state your conclusion in terms of the original problem. There is insufficient statistical evidence to reject the claim that 93% of computers have antivirus software. Did we just prove that 93% of the computers have antivirus software? No, we did not, because that's what we assumed to be true. We just said we can't prove otherwise. Doesn't mean that there are. We just can't claim it at this time. For the critical value method, what we would do is we would look at our critical value here, 1.96. Where did the 1.96 come from? Inverse norm, it's a two-tailed test, 0.025 equals negative 1.96, and because of symmetry we also have the positive one. This is our critical value. Our test statistic up here we said was 1.56, and 1.56 is closer to the mean, to z equals 0, than our critical value, so we would, based on the critical value method, we would fail to reject the null hypothesis as well, because our test statistic fell right here in the clear. The conclusion's the same. I'm not going to write it down again. The confidence interval method is not as strong, but I'm going to review just how to find a confidence interval on the calculator, just to refresh our memory. So we hit stat, we go over to test, and this is a 1 proportion z interval, which is at letter A right here, to create a confidence interval. X is 380, N is 400. What is our confidence level going to be? 0.95, because we're testing at a 5% level of confidence, and this is a two-tailed test. So my 5% is already taken care of because it's a two-tailed test. Only when it's a one-tailed test do we have to double that. And this is our confidence interval. That's probably going to be the most challenging thing to keep straight out of this section when you're using a confidence interval. Draw the picture so you can see how many tails you have. The confidence interval with the alpha equals 0.05 is going to be the same thing as this two-tailed test. It's going to give us the same middle 95%. There's our confidence interval. Would we reject the 0.93 null hypothesis? Nope, it's in there at the low end, but it's in there. We would still fail to reject the null hypothesis. And I'm not going to write everything down again because I did it once already. And that wraps up section 8.3.